Well, welcome everybody. Thank you all for attending. I'd like to thank you. This is a presentation that is traditionally done for industry, but the BBRSDA decided that the members could benefit from this University of Washington Fisheries Research Institute overview of all sorts of different topics that our science team works on diligently on our behalf. My name is Michael Jackson, or MJ, the current president of the BBRSDA. And on the panel today, we have Chris Boatwright, Dr. Daniel Schindler, Dr. Curry Cunningham, Dr. Ray Hilborn, and they'll be presenting individually in a collective presentation. But I just want to let you know that we're really fortunate to have access to this team of scientists. They have a pretty unique ability to translate their scientific research into practical applications that we fishermen can use and understand. And that's a talent. They don't just crunch numbers and print it out. They're able to make that relevant to all of us. So I really appreciate that. And they're passionate about their work, and that passion drives that professionalism. They actually care quite a bit about where they are and what they're doing. I've witnessed it firsthand, and it's something to see. They wake up thinking about it, they go to bed thinking about it, and every minute they're up there, they're thinking about how they can improve the science for the benefit of the fishery. So thank you all for that. They have the awesome responsibility of developing sound scientific research to keep Bristol Bay the most sustainable salmon fishery on the planet. And how can I say that? Because we keep setting run records. Nowhere else can say that. So I'll pass this off to Frances Bursch, the BBRSDA Program Director, and she'll do some introductions.
Thank you. We're going to start with Dr. Chris Boatwright, is the Program Manager and Research Scientist with the University of Washington Alaska Salmon Program, and will be starting us off with the 2022 Bristol Bay Forecast Review. Next, Dr. Daniel Schindler, Professor of Aquatic Fisheries Sciences Sciences at UW and core faculty with the University of Washington Alaska Salmon Program, will present the state of climate in the North Pacific and Bering Sea, followed by a comprehensive review of the University of Alaska Salmon Program and Alaska Department of Fish and Game collaborative study on the changes in age and size of Bristol Bay salmon. Following that, Dr. Curry Cunningham, professor with the University of Alaska Fisheries and Ocean Sciences and the University of Washington Alaska Salmon Program, will present on the application of machine learning methods to predict Bristol Bay salmon run timing. And then to finish us off, Dr. Ray Hilborn, professor at University of Washington and core faculty with the Alaska Salmon Program there, will present on the Bristol Bay Salmon Life Cycle Assessment Project and comparison of the environmental impact of Bristol Bay sockeye and farmed Atlantic salmon. So thank you all very much, and take it away, Dr. Boatwright.
Thank you, Frances. And thank you to everyone who's taken the time to join us today. I'm gonna see if I can share my screen here. Okay, I assume that everyone can see my screen. Let me see if I can move this out of the way. Okay. Okay, so I'm gonna do a, let me see, can I move this? Is there a way to move this bar?
It's good, Chris, you don't need it, it's fine. You don't need to tinker with it.
So I'm gonna start us off with a review of the 2022 University of Washington FRI preseason forecast. And I typically like to start a review of the preseason forecast with the most basic forecast table we generate. And so what we're looking at here on the screen is a forecast table. In the body of the table, it shows 36 individual predictions. Those are organized by the Bristol Bay's 9 major river systems, and a prediction for each of the dominant 4 age groups of salmon that return to those river systems. So that's 1-2s for sockeye, that's 1-2s 1.3s, 2.2s, and 2.3s. And so these individual predictions sum to give us a total Bristol Bay forecast of 71.91 million sockeye expected back in 2022. So next, I'd like to take a step back from the forecast table and take a look at the primary data set that goes in to the forecast is built on. So what we're looking at here is a graph of Bristol Bay sockeye salmon returns from 1963 to 2021. Really, this is just a history of Bristol Bay in terms of the return of adult sockeye. So I'm gonna move over to the far right-hand side of the graph here and look at this most recent string of record-setting years for Bristol Bay sockeye returns, 2015 to 2021. And really, these really big years of sockeye returns in Bristol Bay are characterized by diversification of returns across river systems. That's to say that strong returns to all of Bristol Bay's river systems. And indeed, looking at last year where we exceeded 70 million sockeye in the return, to get to that number, it almost certainly is going to be built on strong returns across all the river systems. So it is specifically this return data coupled with the specific age data for sockeye to the river systems that is the primary data set that goes into the forecast. However, now that we use some machine learning models in some of these predictions that go into the forecast, we have now formally incorporated data sets such as sea surface temperatures and abundance of other salmon species during Bristol Bay sockeye ocean phase of their life history. But specifically, we are interested in the next chapter here, so to speak, and that is the 2022. What's expected, how many sockeye are expected back to Bristol Bay in 2022? So that brings us to the forecast table as we release it each November. This on the left-hand side here, that's the part of the forecast table we've already looked at. It's the 36 individual predictions organized by the 9 major river systems and the 4 dominant age classes of sockeye to Bristol Bay. Again, our 2022 expectations are 71.91 million sockeye. Added to this table to the right of the river totals is an estimate of escapement by river system, given run sizes of the size that we have forecasted for each river system. To the right of that is an estimate of the Bristol Bay fish taken in the South Peninsula catch. And then we take both of those, the estimate of escapement and the estimate of the South Peninsula catch, we remove those from the river total and we come up with an estimate in millions of fish here for inshore harvest of sockeye. So for a total run size of 71.91 million sockeye expected back, we would expect an inshore harvest of 52.4 million sockeye. So using those numbers of fish estimated in the inshore harvest, we then take that number of fish and we translate it into a University of Washington FRI preseason forecast in pounds. So for the forecast in pounds, we organize this by the 5 commercial fishing districts, again by each of the 4 dominant age groups of sockeye to Bristol Bay. And so for an estimate of inshore harvest of 52.4 million sockeye, we would expect 252 million pounds. Now, to get to that total in pounds, we have to use, let's see. So we used so the size of sockeye that is seen in the harvest is overwhelmingly a factor of ocean age. So to come up with average weights of sockeye, we lump 2 ocean fish together, so 1-2s and 2-2s, and we lump 3 ocean sockeye together, 1-3s and 2-3s, and we used 4.1 pounds and 5.6 pounds as those average weights. Those are, on average, those are small sockeye, as I'm sure most people listening to this are aware. So one thing I thought I would do, I thought I would bring up kind of the basic data set that looks at Bristol Bay sockeye size over from 1980 to 2021. It's the graph that's popped up here with a black background. It's simply Bristol Bay sockeye size in pounds. The orange data points connected by orange line that's on top are the average annual weights of 3 ocean sockeye to Bristol Bay. And the blue data points connected by a blue line are the annual average weight in pounds of sockeye back to Bristol Bay. And so really we can see that since the onset of these really large runs that exceed 50 million, and in a number of these years exceed 60 million, from 2015 to 2021, we really have been looking at, on average, very small sockeye, and in particular, these last couple years where 2 ocean sockeye have really hovered around the 4-pound mark, and 3 ocean sockeye right at about the 5.5 pound or just above mark. So moving from that, kind of the forecast in pounds, to a third table we release with the FRI forecasts each year. It's a lot of information here, a lot of basic information is provided in this table, a lot to look at on the screen. But again, we go back to organizing this table by the 9 major river systems. To the right of the river systems in red, we have the 2022 forecast values for each of the river systems. Next to that, we provide the 2021 forecast values, so last year's forecast. And then the 11 columns after that are actual returns by river system, or observed sockeye returns in each of the 11 prior years. This, of course, this table is a very quick and coarse way to look at the last year's forecast performance. And though we had what we thought was a very large forecast at 51 million sockeye, the run came in exceeding 70 million sockeye. And as no surprise, we generally under forecast river system by river system. Igigik was the only river system that underperformed or did not come up to expectations. So a little bit more specific look at forecast performance across the time series of 2000 to 2021. This is a 2-panel plot, the top panel here with red columns and blue columns are percent deviation in the forecast from actual returns. The actual returns year to year across this time series are set to the 0 line, and red columns that fall above the 0 line would have been over forecast in those years, and blue columns that fall below the 0 line or the actual returns would be under forecast in those years. So across from 2000 to 2021, the percent error in the forecast, or specifically the mean absolute percent error, is 15.6%. So one of the things I wanted to do over the last couple of years is go back and really specifically take a look at this string of really big returns to Bristol Bay, really record-setting returns, and kind of break out this forecast era and take a look kind of specifically at where it falls. The two black background panels or graphs that have popped up do the same thing. The one on the left simply uses all the data, return forecasted numbers and return numbers of sockeye salmon to Bristol Bay from 2014 to 2020. And so what I've done in the blue columns are total forecasted sockeye. This is done by the 4 dominant age groups, so 1-2s, 1-3s, 2-2s, and 2-3s, and plotted that against the orange columns, which are just the total number of observed sockeye or actual sockeye returns. And so for this period here, 2014 to 2020, reasonably consistent under forecast in those years. Most of that forecast era was caught up in greater than expected 1-2 production. Now, the thing that made this a little bit more tricky to deal with and get a hold of is that the fact that these 1-2 events, or this greater than expected number of 1-2s, really occurred in multiple year to year in different river systems, but in multiple, but not the same river systems. In other words, we saw much greater than expected 1-2 production in the Wood River system in a couple of these years, in the Naknek River system, the Igigik River system, and the Kvichak River system. So given last year's record return, I wanted to break this out on its own, and really the story is quite the same, that the overwhelming bulk of this forecast era again came in the 1-2 age class of sockeye. And in last year, this was predominantly in the Nushagak River system, but to some degree as well in the Wood River system again. So this is simply just going back to the forecast table that we've already looked at as we release in November. And I thought I would just point out that this big 1-2 production we've seen across these really big years is reflected in some of the forecast numbers in this. Obviously, in this year's preseason forecast, we have reasonably large forecasts both for Nushagak 1-3s, so that big 1-2 event in the Nushagak River. Nushagak River 1-2s are the primary predictor variable for Nushagak 1-3s. So we see a large forecast of 3 ocean sockeye back to the Nushagak River in 2022. As well, a relatively large forecast for Wood River 1-2s, as simply over this time period of really large runs, the Wood River has had generally greater than expected production of 1-2s. So with that, I'll stop, and our group can try to answer any questions folks might have.
Thank you. And I forgot to mention it when I was speaking, but please go ahead and type any questions into the Q&A section, and the presenters will address them.
I'll stop sharing.
Oh, we have a raised hand here. Stephen Miner here, you should be able to speak now. I don't hear you, Stephen, but if you have a question, go ahead. I see a question in the chat or in the, yeah. Alyssa Brackenhofer asked, what are thoughts on the reasons for higher return of 1-2s?
You know, Daniel is just about to give a very detailed talk on the changes in size and age classes and production in age classes of Bristol Bay sockeye. But generally, I think it has to do with very climate-driven ocean growth and very fast growth of sockeye has just generally shifted a larger proportion of the run to younger fish or 1-2s.
All right, a couple more in the Q&A. A question from Mike Hyde. Is there a theory why the Kvichak dropped so much over time as a percentage of the total and the Noosh Wood system increased so much?
You know, Daniel, do you have any thought on the reduction in Kvichak and the west side becoming more productive?
No, that's a mystery, I think, that will never go away. I mean, I think what we do know is that climate change has warmed up the lakes and juvenile fish are growing faster in lakes throughout Bristol Bay. But why the Kvichak declined and stopped cycling and why the west side systems have picked up is a mystery for sure. The fact that the last couple of years, most of those west side stocks did well suggested some nearshore coastal ocean issue, but I don't think anyone knows, and we probably will never know.
Okay. Let's see, there's one more question from Eric Beamer. It says, are there district-specific patterns of forecast error over under? If so, what? Oh, Curry's typing the answer to that one. I'll let him answer that. Typed there. And then a question from Todd Overby. I wonder if we aren't artificially selecting for smaller fish with our mesh size.
Yeah, I can answer that one. We've, I'll give a talk here in a second about the analysis we've done quantifying the long-term changes in size of fish. And it turns out that the selectivity is pretty small, and it really depends on the district. And in general, if there is a bias in terms of which fish are caught, they tend to catch bigger fish. You guys tend to catch bigger fish, but it's mostly in Ugashik. In all the other districts, the difference between the sizes that escape to the watershed and the sizes that are caught in the fishery is biologically not significant. So even though that is a worthwhile concern, the data don't suggest there's a really strong evolutionary selection for smaller fish.
Thank you. That's all the questions I see at this time.
All right, I guess I'm up next. I'm Daniel Schindler from UW, and I'm going to give two quick summary presentations. One is about the state of the climate in the Northeast Pacific and what the forecasts are for this coming summer. And then a second is what I just mentioned, which is this analysis of long-term changes in Bristol Bay sockeye size. So to look at the climate, just going to start by orienting you to a map of sea surface temperatures in the Gulf of Alaska and in the Northeast Bering, which of course is Bristol Bay. Here's Alaska. Here's the Alaska Peninsula coming out. And what's plotted here are what we call anomalies, which is the observed difference relative to the long-term average for that site at this time of year. And things that are orange and red mean they are, in this case, in the red case, 2.5 degrees above normal for this time of year. So this is for the summertime temperatures relative to the long-term average. Yellows are a little bit 1 to 1.5 degrees above normal. White means it's about average. And basically showing you this map is that for the record returns that we've seen in the last 5 or 6 years, those smolts left the rivers in Bristol Bay for the ocean between 2014 and 2019. And what they encountered were warmer than average coastal sea surface temperatures. And this corresponds well with what we know previous to about 2000, shown in the bottom left here, which is the same anomaly plots for the 10 best years in the last 60 for Bristol Bay in terms of smolt survival. And the basic message is, for Bristol Bay, warmer spring sea surface temperatures translate into higher survival and bigger returns 2 and 3 years later. So these big returns we've seen recently have come off of smolt years where the smolts hit warm temperatures in the coastal ocean. And then they had warmer than average temperatures in the Gulf, which is where they're putting on most of their growth in subsequent years. 2021 was generally in line with this pattern, but what we started to see was the beginning of cooling off. So here's the same map, but this is just for last summer's temperatures. Bristol Bay, instead of being red, is now yellow, which is about 1 degree warmer than average. And you can see that the Gulf of Alaska last summer is white, which means it was bang on the long-term average. And there were some areas that were actually blue, which is colder than average. So we finally saw the end of those warm blobs that you may have heard about, which were these literally off the charts hot water temperatures between 2014 and 2019. And for people fishing for salmon south of the Alaska Peninsula, that was correlated with nearly disastrous returns everywhere. And of course, for Bristol Bay is where we saw those record returns to rivers from Bristol Bay. And to put this in a long time series, these are data for the Eastern Bering Sea between 1950 through to 2021. And here's this sequence of relatively warm temperatures in the last decade. And 2021 is not down to average, but at least it's back to closer to where it has been over the last 60 years or so. For the Gulf of Alaska, we see the same general pattern. It bounces around from year to year, but again, these really warm temperatures here. You know, NOAA literally had to rescale the axes on their graphs to accommodate these new observations. So these are those warm blobs that Bristol Bay fisheries persisted through and maybe actually benefited from. And one of the questions, of course, is, well, why did the Gulf of Alaska rivers do so poorly while the Bering Sea and Bristol Bay systems did so well? And it's important to note that even though there is year-to-year variation in temperatures in the Bristol Bay and the Gulf of Alaska, the Gulf of Alaska is always a couple degrees warmer than Bristol Bay. So this run of exceptionally warm years may have been too warm for high survival of sockeye entering the Gulf of Alaska, whereas Bristol Bay fish are still in that sweet spot of temperatures that are neither too hot nor too cold to allow for high survival rates. So what's it going to look like now and in the future? So this is for the last week of April, just a few days ago. Again, a map. This is for the whole Pacific Ocean in this case. This is the part of the map we should be concerned about. You can see that it's white. So things are generally average or a bit of blue, a little cooler than average the last week of April of this year compared to historical averages. The offshore temperatures are warmer than average, but typically the Bristol Bay fish aren't really encountering those warm water features farther offshore. NOAA also produces, last thing I want to mention is right here along the equator at 0 degrees latitude, is a big a big blob of cool water. So it's blue. And this is sort of the fingerprint of a La Nina. So typically the signal of La Nina is cold tropical waters in the Pacific. And this La Nina pattern that we've seen was the strongest observed in the last couple of decades. And it was strongest last year, and apparently it's starting to weaken right now. But it's not El Nino, which is what most people are most familiar with. But yeah, the last couple of years, we've been in a La Nina, which is starting to dissipate. Looking to the future, looking to this summer, this was a forecast from, I think this is NOAA, for May, June, July. This was issued in April, so about a couple of weeks ago. And basically you can see the forecast for Alaska is cooler than average. So blue means the odds are in favor of a cooler than average temperature. Most of the US is predicted to be substantially warmer than average, but Alaska is affected by different climate conditions. And the expectation is for cooler than average or average coming into the summer. A similar forecast is also produced for the sea surface temperatures. And this is for, again, sea surface temperature anomalies, which is the difference from the long-term average. And again, zoom in here on coastal Alaska, things are blue. The expectation for June, July, and August of this coming summer is for cooler than average water. So again, just to reiterate, the big returns of Bristol Bay sockeye we've seen in the last decade came off of those really warm, hot water temperatures in coastal Alaska. And those have cooled substantially, and the forecast is that they will spill into this coming summer as well. And for those of you who are in Alaska, you know that it's been a pretty cold winter and early spring so far. So those conditions are expected to persist into the summer. So the outlook, yeah, again, I mentioned this, these early, very warm summers, 2014 through 2021, have basically dissipated because of the strong La Nina, and cool temperatures are expected to persist through this coming summer. They haven't made forecasts beyond this coming summer. Okay, the second piece I'll talk about is something Chris alluded to a little bit, which is an analysis we're doing, or we're finishing up, on the long-term changes in Bristol Bay sockeye body size. Most people on the water are knowing full well that the fish seem to be a lot smaller than they used to be. So the purpose of this project is really to quantify those changes and ask what those changes are correlated with that may provide explanations for why fish are so small right now. And basically, this is what we did, was took over 2 million observations from Alaska Department of Fish and Game. And those data need to be cleaned up. They were kind of a mess, just with database errors. They need to be accounted for in terms of which fish are caught in catches versus which fish are caught in or enumerated in escapements. And then you need to also account for the various run sizes and age compositions to each of these rivers. So lots of analysis here, but this top panel really shows what we're interested in, which is the mean size of fish that have returned either to Bristol Bay in this top left bin, or each of the major river systems. And you can see for Bristol Bay, the size of fish actually increased and then stabilized till about 2005. And it's really these declines in body size are mostly accentuated in the last 5 to 10 years. And depends on the river system. Things like the Wood have shown the biggest differences. Things like the Nushagak have wiggled around, but have been arguably stable. So we dug into these a little bit to ask how big are the differences and what might be causing them. So what goes into those analyses is changes in the stock composition. So this is similar to what Chris showed, that different rivers have been stronger and weaker in the past. So we account for that. And then we account for the fact that the growth rate of fishes has changed. And if you look at the time scale here, these are based on brood years, and the blues are fish that spent 3 years in the ocean. The two check and 1 check smolts, and the oranges and yellows are fish that spent 2 years in the ocean. And so the 2-year-old ocean fish are always smaller than the threes. But what you should see here is starting about 1980, the sizes of these fish for their age started declining. And in fact, these declines are accentuated for three ocean fish. So we've seen, there's been, 40 years of declining side growth rates of sockeye salmon in Bristol Bay. On top of that has been changes in the age composition. So these are all the major rivers on the small panels. The big panel is the aggregate for all of Bristol Bay. And what you see is that in blue are the three ocean fish. They actually increased in abundance for most of this time period between 1960 and the present. And it's only the last few years that we're getting the shift back to two ocean fish that Chris was alluding to in the forecast summary. So between about, let's call it 1965 brood year and about 2005 brood year, there were more three ocean fish in Bristol Bay runs than there was either before that or in recent years. So we account for this in our analysis. Do this on a brood year basis. We wait for catch and escapement by river. We basically subsample the data and reconstruct what the runs would have been, which turns out to be more than 2 billion data points. And then we ask, well, how big are the trends? What's causing them? So what this graph does is compare the first 5 years of the time series, so 63 through 68. And we ask how much different are they in the last 5 years of the analysis in terms of average size of fish returning to Bristol Bay. And what we see here is that the average size at the scale of Bristol Bay is about 20 millimeters smaller in total length. So that's about an inch shorter, okay? And then we ask, well, how much of that is changes in growth rate, which is shown in blue, and how much of it is due to changes in age structure towards younger fish? And you can see at the scale of Bristol Bay, about 85% of the reduction in fish size is because of slower growth rates. And only a small fraction is because of younger fish. That distribution changes from district to district. So in the case of the Wood, we've seen about 35 millimeters smaller fish in the recent 5 years compared to the 60s. And about half of that is due to a declining growth rate, and a half of it is to more fish coming back as two ocean fish. Interestingly, in the places like the Nushagak, there's been almost no long-term change in average body size. And that's because the slower growth rates of fish in the ocean is offset by more three ocean fish coming back. So the net effect is close to zero. Same thing is seen in the Kvichak. The net effect is pretty small because there are more older fish than there were historically, and that offsets some of the slower growth rates. So pick your river, and you can see that basically the blue bar is invariably bigger than the gray bar, which means growth rate's the dominant thing that's been slowing down. And in some cases, it's offset towards larger fish. And we can see this in this somewhat complicated figure, but just look at the big panel. This is 1960 as the beginning year, and we set that to 0, and we compare every subsequent year to 1960. And red is the average size of fish coming back to rivers in Bristol Bay. And you can see that in the 70s and 80s, fish were bigger than they were in 1960. They declined to about 1960 levels by 1990. Then they got big again till about the 2000 brood year. And then we saw this slow march back towards 1960 values. And then the last 5 or 6 years is where the bottom fell out. In blue is the expected sizes based on the growth rate alone. And what you can see is the fish would not have gotten as big as we observed, and then this decline would have started earlier. So the fact that the observed change is different than the observed growth rate change means that this difference in gray is because of more old fish returning to rivers. And it's only in this last couple of years, which happened to be the years that Chris pointed out where we under forecasted two ocean fish. This is where like I say, the bottom falls out because we're getting big returns of two ocean fish on top of really low growth rates. And that's why the last couple of years the fish have really been tiny. So we can assess, well, what might be causing these long-term changes in growth rate of the fish. And these are the four statistically significant effects that we can detect in a time series analysis. One is Bristol Bay sockeye abundance alone. And what you can see is when the return is big, particularly bigger than about 40 million, the average fish size is much smaller. So there's a negative relationship here. And of course, we're seeing this buildup of Bristol Bay sockeye since the 60s. This string of big years is associated with slow growth rate of sockeye because they're competing with each other for food. Superimposed on that is the fact that there's been this big buildup of pink salmon and chum salmon in the ocean. I'm showing just pinks here, but this also has a strong negative effect. And it's accentuated when you get to pink salmon abundance over about 500 million fish out there. And that seems like a big number, and it is a big number, but that's the reality we often forget about is the North Pacific has been full of pink and chum salmon from hatcheries now, particularly since the 80s. And these fish appear to be competing strongly with Bristol Bay sockeye. There's some climate signals that show up as well in their analysis. Warmer sea surface temperatures tend to have a negative effect on growth rate. And interestingly, warmer winter sea surface temperatures seem to boost growth rate. But the question is, where are we now? And this sort of summarizes it entirely. So the size of the dot here tells us what the relative size of the fish is. And smaller dots mean that fish are smaller than the average. Bigger dots mean that they're bigger than the average. So these are all the different years as dots. And then on the horizontal axis is the size of the Bristol Bay run, sockeye run. And on the vertical axis is the pink salmon abundance in the ocean. And then the color tells you what years we're talking about. So in the 70s and 80s, you can see we're down in here where sockeye abundance in Bristol Bay was pretty low. Pink salmon's abundance was pretty low, and all the dots are big, which means in general, fish were quite large. And through time, we've slowly marched our way to the top right portion of this graph. Now, most of the dots are relatively small. And these are years that have high sockeye abundance and high pink salmon abundance. So basically what the argument is there's just a lot of competition out there in the ocean right now, both within Bristol Bay sockeye and between Bristol Bay sockeye and hatchery produced pink salmon. And this could have pink salmon plus chum salmon. The two went up pretty well the same with each other. So we've only shown pink salmon here. But if we look at the forecast for next year, Chris showed it's up around 72 million. Pink salmon abundance is high out there right now. We should be expecting a lot of small fish this coming summer. And then the last thing I'm going to mention, I'm not going to show you anything from it, but it turns out that because this relationship between run size and fish size for age is so strong, we're working on methods to include that in our within season forecasts of run size. And it looks like by the last week in June, we can come up with a pretty strong prediction of how big the run will be based on the size and age of 3 ocean fish. So if you see a lot of small fish in your nets early in the season, chances are the forecast is going to hold up and there's going to be a big run. And that's all I have. I'm happy to answer any questions.
Thank you. There are a few in the Q&A here. One asks, John Lonnie asks, given the historical predictions, actual returns to the Kvichak have been accurate, is there any chance ADF&G management of Kvichak will allow earlier harvest? Waiting until 2 million escapement numbers reached guarantees fleet behavior that doesn't allow for efficient fleet spread early in the season.
Yeah, that's a good question, John. I think that's one you should really pose to Fish and Game. Yeah, there's lots of complexities in how they manage that district, and yeah, you should push that on the manager and see what they say.
And then from KS here, from your work, what relationship do you see as the sweet spot for temperature in regards to fish survival and excelling expectations? Where is the danger zone?
Yes, this is a really good question. Basically what we have seen is as climate has warmed up, Bristol Bay lakes have warmed up, the coastal ocean in Bristol Bay has warmed up, and both of those two things have continued to produce more and more sockeye. And that seems to be associated with higher smolt survival. The issue, of course, is that at some point we tip off the other side of that curve. And the question is, how warm is too warm? And if we use the Gulf of Alaska as an indicator, it looks like about 13 to 14 degrees is where at least those stocks have not performed particularly well. And Bristol Bay is still a couple degrees colder than that. So yeah, we're heading towards a warmer future. There's no question about that. We don't know where the tipping point is where things are going to collapse. Pinks and sockeye, they have slightly different food sources, but the reality is they have a ton of overlap. They're very generalist. Both pinks and sockeye will eat everything from little tiny copepods to amphipods to a lot of larval fish. And if you use isotopes to assess their dietary overlap, it turns out they're smack dab on top of each other. So there's a lot of competition between pinks, chums, and sockeye, even though we tend to think of them as different species who eat different fish. The bulk of their food has a high degree of overlap between them. Yeah, sorry, I'm interrupting here, Francis, but I'm just reading the questions, if that's okay. Yeah, the pinks and chums in the ocean here is the North Pacific. And the reality, what we can do is we know how many fish are coming back to hatcheries or caught in fisheries, or we also know how many smolts are released from fisheries. We don't have a good sense of where specifically they go in the ocean, so we just add them up to the North Pacific, which is mostly the Gulf of Alaska and the Southern Bering Sea. All right, KS. I have no clue who you are, but are there any studies available to describe catch efficiencies for various small salmon per mesh size? Yeah, this is from Luke. There's lots of data and previous studies that have looked at catch efficiencies of salmon for different mesh sizes. And, the reality is those selectivity curves, as we call them, do have a peak where there's an optimal size for matching the fish size to the mesh size. But, the efficiency curves are fairly broad. Generally, smaller meshes catch smaller fish. Last year, if I remember correctly, Michael Link and his group put out an analysis of catch efficiencies from Port Muller fish. Yeah, I'd be using smaller mesh this year if I had the choice. Sam Raybung says, it seems the number of hatchery-produced pink and chum salmon released in the North Pacific hasn't really changed since the mid-1980s. That doesn't seem to line up with the graph. No, if you look at the graph, Sam, I can show you that the number of hatchery-produced pink and chum has been stable since the late 80s. And we can go back to the graph if you want, but superimposed on that has been the buildup of sockeye. So if you look at the total number of hungry mouths out there, you have to add that huge bolus of 500 million pink salmon, plus almost as many chum salmon, and then this buildup of sockeye on top of it, of wild sockeye on top of it. So the number of hungry mouths, and I can go back and show this, it's a really important question. The buildup of hungry mouths is as high now as it's ever been. So here's the buildup of sockeye from Bristol Bay here, in the bottom left. And here's the buildup of pink salmon, which continued to increase until about, depends on where you draw the line, but let's call it 2010. And these are pink salmon from Alaska, Russia, and Japan. And then superimposed on that are chum salmon from Alaska in particular, but also Japan and to a lesser extent, Russia.
Daniel, I think a key point there is it's not just the increase in hatchery releases, which have been pretty stable, but the pink and chum have also been surviving better. So it's a combination of the hatchery release increase in the early days and then just better survival leading to more hungry mouths.
Yeah. There's more salmon biomass in the North Pacific now than probably ever in the past. And a huge fraction of that are hatchery produced fish. Does the pendulum swing the other way once the growth rate slows down? Do we see a major decrease in run size shortly after the big ones? Yeah, this is an interesting question as well. You know, how growth rate corresponds to survival rate in the ocean is not really a clear one-to-one relationship. So yeah, clearly there's slower growth, bigger runs, but there's been, you know, the opposite has been true as well. So yeah, I don't think there's a clear answer to that question. There's no evidence that we're looking at some long-term cycle oscillating back and forth. All right, we want to move on to curry. Oh, I just want to say that if anyone wants to email me or any of us, feel free to go ahead and we can follow up offline.
Excellent. Well, thanks, Daniel. I'll take over here and let me get my laser pointer going. So let me share my screen again. Excellent. Well, I'm always excited to give a presentation or chat with the fleet. As a former Bristol Bay commercial fisherman, it's exciting work, and I'm excited to be here today. So thanks for taking the time out of your busy schedules as you prep for the season to sit down and take part today. So I'm going to be talking about some of the work that we have ongoing that was funded by BBRSDA to look at whether or not we can apply some machine learning methods to get a better handle on whether or not we're likely to see early or late run timing from year to year for sockeye returning to Bristol Bay. And to start, I always like to start with a couple definitions. So I'm going to be talking a lot about run timing here. And when I say run timing, I'm going to be talking specifically about the midpoint of the run, or the date at which 50% or about half of the season total catch and escapement has been seen and counted inshore. So when I say early or late run timing, I'm talking about earlier or later than the average for a given river system. So just to start off, what these are for each of the Bristol Bay fishing districts, this is the distribution of median dates or halfway dates for catch and escapement for each of the major fishing districts. What we see over here and the distribution across years in terms of when we see that midpoint date or that median date. So not surprising to anyone here, you know, Igigik tends to be the earliest. Usually we see that 50% date or that midpoint date around July 5th or so. Nushagak just slightly later, July 6th or 7th. Naknek, Kvichak, you know, we're talking about July 7th to 8th. Obviously, it's been somewhat more variable in recent years. Ugashik substantially later, usually seeing that midpoint date around the 12th of July, and Togiak after that. So throughout my presentation, when I say run timing, I'm talking about that 50% date or that midpoint date for the run in each year. So the question is, how has run timing varied over time here for Bristol Bay as a whole? So what I plotted here, each point is an individual year from 1970 moving forward. And what this shows is the run timing relative to what we might think of as average run timing. positive values being days later than the average in terms of run timing for that halfway point, negative values being days earlier than average for that midpoint date. And what we see, first off, like many of these things, it's highly variable over time. It bounces around, it goes back and forth. We've seen years here where the run was on average to Bristol Bay as a whole about 5 days later than the average. We've seen years when it's been quite early. But over the history of Bristol Bay, we've seen a lot of variability. One thing to note is that in the recent past, we've also seen these sort of two pronounced periods of consistent on time or early run timing to Bristol Bay as a whole between 2009 and 2014. And then in this more recent period, so as Daniel talked about, this recent period of high production, kind of 2015 and forward, we've seen on average late run timing to Bristol Bay as a whole. So in addition to this variability from year to year, we've seen some consistent patterns recently, or at least somewhat consistent. We can look at this same sort of information, again, days late, days early as negative values across time. What we see in 2019 was this extremely late apparent run timing to the Ugashik district. In both the Igigik and Naknek-Kvichak districts, this high production period after and including 2015 has also, when I say high production, high catch and escapement, high abundance years have coincided with, on average, later run timing compared to the preceding 4 to 5 periods here in sort of the 2009 through 2014 period. So this gets to the root of the project here and the root of the question, why do we care about run timing? Well, there's a couple of reasons. One, a lot of people want to know when to have their boats in the water and whether or not, if we have an early run coming, do you need to be ready earlier? On the processing side, folks want to know when to have processing crew trained, ready, and ready to process fish that are coming in. From my side, so as Chris talked about and Daniel talked about, we have a role in terms of in-season run size forecasting for Bristol Bay, trying to predict in-season based on the data that are available, how many fish are coming back and where they're going. Our in-season run size forecasts, or our predictions for run size based on in-season information, end up being pretty sensitive to run timing. If we have, an early run, that is to say, we have more fish than we expect early in the season coming through the fishing district or seen as escapement, it adds a lot of uncertainty in terms of whether or not we have a large run coming, or if in fact it's a normal sized run and the fish are just early. So run timing influences our ability to accurately predict run size in season. So getting a better handle on what drives run timing and whether or not we can predict it prior to the season or even during the season has some value. So you'll saw in my title that the particular branch of sort of methods we're using to predict run timing are what we might think of as machine learning methods. And I'm sure everyone has heard of the term machine learning. Machine learning is now and is likely to remain an important part of our lives, whether or not we're talking about weather forecasts, whether we're talking about, when you log on to Amazon and it recommends things for you to purchase, whether your email suggests who you should be emailing back, or whether we're talking about stock markets and trading. Machine learning plays a role in many aspects of our lives, and increasingly so over time. So our question is whether or not we can leverage some of these methods, given the data we have available, to address this question about whether or not we can predict whether or not sockeye are going to be early or late in terms of when they arrive in shore to Bristol Bay. So within the broad umbrella of machine learning methods, there's a couple general categories. We're over here in what we think of it as sort of supervised machine learning methods. And these are mostly used for regression in this case. So trying to predict a sort of continuous value, number of days early or late, as we were looking at before, or classification. Trying to predict, are we, one side of the coin or the other? Are we early? Are we late? Or are we on time, early versus late? So we're in this supervised machine learning end of the spectrum in terms of what we're talking about today. So the core objectives of this project are really to identify whether or not there's environmental conditions that are associated with run timing or have been associated with early or late run timing historically. And generally, these environmental conditions should be linked to something in the ocean related to feeding or migration pathways, or where sockeye are residing prior to when they start that return migration. It always amazes me that we have these sockeye out in the open ocean at some point in that winter or spring of the year that they're returning. So the fish that are returning here in 2022 in the coming weeks and months will have, or are starting that return migration, likely have already started. And in order to arrive over that core 2 to 3 week window that we see in Bristol Bay, you have to know a couple things, which is pretty amazing. One, generally where you are in the ocean and how long it's going to take you to get back. And so where that mass of fish is out in the North Pacific, and whether or not that's driven by marine environmental conditions, might dictate whether or not we see fish arriving a little bit early or a little bit late. The second objective is to really identify or develop a sort of sound workflow to automate how we compile the environmental information and the salmon data, the salmon run timing data, to easily implement forecasts in the future. Now, this sounds kind of trivial, but as we talk about the environmental information that's out there and available from NOAA and NASA, particularly satellite-derived data products, these come from a lot of different sources. So coming up with a standardized way to pull all that in easily at the beginning of the season to make these predictions has a lot of value, although it may be a bit time-consuming. And of course, we want to explore a couple different flavors of machine learning methods for predicting run timing and see which works better, which doesn't work better, and how well, in fact, they do work. So in terms of the environmental conditions or environmental processes that we set out to look at, one is ice conditions in the Bering Sea. So Daniel touched on this a bit, but over time, we see pretty high variability in ice conditions, both throughout the winter and coming into the spring. So here, what I have is sea ice extent on January 15th. So this is the 2004 to 2020 average. This is 2018. There was a much smaller ice pack or smaller ice extent as of January 15th, 2018 versus 2019, 2020, and 2021. So over time, from year to year, we tend to see a lot of variability in where the ice pack is, and that depends a lot on the date. In some years, we have a large ice extent, but we get strong winds and warm temperatures out of the sort of south and southwest, and that ice pack recedes quickly. And that may have some predictive potential for run timing when we think about Bristol Bay sockeye returning. Of course, there's the absolute sort of sea ice extent we see over time. So what I have plotted here is sea ice extent. Each of these lines is an individual year going from November all the way to June. Of course, we see our maximum sea ice extent sometime in March into April. So that black line is sort of the median, or kind of the long-term average. In blue is kind of where we are, at least as of the beginning of May. We saw, on average, a similar sea ice extent to the long-term median, if not a little bit more here as we got into the beginning of April, and we've rapidly declined in terms of the sea ice extent. And this is very different than what we saw last winter, in the winter of 2020 to 2021, here in green, which is basically lower than average sea ice extent throughout the winter. The other key environmental processes that we set out to look at are things that we all sort of think about, one of those being sea surface temperature. So this is a snapshot of sea surface temperature right now, and Daniel talked quite a bit about this as well, but right now we're seeing, this mass of water out here. This is about 0 degrees Celsius out here, down to about 58 degrees latitude. Below that, we're seeing some 3 degree, 2 degree temperatures as we move into Bristol Bay. Overall, what we're seeing plotted here is the sea surface temperature across the year from December all the way over into the fall, into November. And that light gray line is the long-term average here. That light blue line is what we saw in 2021, and this black line is 2022. So in 2022, we're seeing sea surface temperatures in the southeastern Bering Sea, so down here in this region, that are pretty bouncing around pretty close to the long-term average. And in fact, quite a bit below the sea surface temperatures we saw at this time of year back in 2021. So last spring and the lead into last year's season. The other processes that or environmental indicators we might want to look at are kind of broad scale ocean climate indices, things that kind of summarize conditions out in the North Pacific at a very broad scale. So things like the Pacific Decadal Oscillation, some of you have probably heard about this before in great detail, that sort of is a general summary of temperature anomalies, warm, cold conditions out in the North Pacific generally. The North Pacific Gyre Oscillation, which generally describes climate patterns and changes in ocean currents and circulation. And then the ENSO, or a different pattern that summarizes conditions out there with respect to temperature, winds, sea surface pressure, things like that. So these are broad scale environmental indices that we use to sort of summarize conditions out in the North Pacific in general that may give us some insight into run timing as well. And the last one that I want to touch on is something that we all interact with, but maybe don't think about, and that's airports. Airports are and have been this wonderful source of environmental information, extending far back before we had large-scale research cruises, in many cases going out into the Eastern Bering Sea, and before we had satellites measuring temperature and other environmental data. Long before that, we had people out there measuring conditions, air temperature, precipitation at our regional airports throughout Alaska and across the world generally. But these are wonderful time series of information on things like temperature and precipitation that we can bring to bear that extend way back, back to the 1960s and even before that. So this is another kind of piece of the puzzle that we were hoping to leverage to inform our run timing forecast. So thinking about temperature, both in terms of average temperature during different month periods in the winter and spring leading up to the season, as well as sort of the total cumulative temperature. We can think about the total number of temperature units that are accumulated over time. And same thing with precipitation. So rain and snowfall, both kind of averages in maybe February and March, or maybe the total that's accumulated over some time period. So with that in mind, turning back to our original goal, we want to in some way evaluate whether or not there's this linkage between Bristol Bay salmon run timing and these environmental conditions that we see. And we want to ask some pretty straightforward questions. Which of these environmental processes or environmental indicators are important or useful in trying to predict run timing? Generally, what is the direction of their association in when we see warm conditions? Does that mean run timing is likely to be early or late? When we see a large ice pack late into the spring, is that generally associated with early or late run timing? And then, of course, how reliably can we predict run timing based on these environmental signals? So as I said before, our goals with this project were to explore sort of a broad suite of different machine learning methods and tools for predicting run timing based on the environment. I'm going to talk about one particular class of methods here. These are boosted regression trees, and I won't go into the detail, but basically what you do is it's a machine learning method where you create these series of complex decision rules. If your predictor variable is sea surface temperature in March, you might have a branch in your decision tree that says, well, if sea surface temperature is above 1 degree out there in some area in March, you tend to see run timing that is early. By some number of days. And you create these sort of branch decision trees. These are then updated over time, and you look for areas where you have poor predictive performance, and you try to train a new decision tree with a series of decision rules that addresses the errors that you saw before. And at the end of the day, the goal is by creating these complex trees and looking across them, we can hopefully get a decent handle on the association between these environmental processes and run timing, as well as what those relationships look like, even if they're kind of highly nonlinear. If it's not a straight linear relationship between temperature and run timing, if maybe it has some complex shape, or maybe you have this breakpoint where below some value of temperature, run timing is pretty close to average, but once we exceed some value, run timing is either early or late. That's one of the benefits of these methods. They can identify these highly complex or kind of nonlinear interactions between run timing and the environment. So I'll jump into an example here. So as part of this project, we've been looking at Bristol Bay as a whole, as well as each of the Bristol Bay fishing districts to try to get a handle on how well we can predict run timing. And so the first sort of piece of inference we get out of these boosted regression tree methods is what we think of as variable importance, which is which of these environmental processes are important in terms of being able to predict run timing for Bristol Bay as a whole. And so the bar here, the height of that bar, or the length to which it extends to the right, is the relative importance of these variables. Which of these are most important in predicting run timing? So we see NPGO, that North Pacific Gyre Oscillation, in November and October of the year prior to the return year. So thinking about the 2022 run timing, this would be the NPGO signal in October and November of 2021. So in last year, air temperature in king salmon during November and December, leading up to the season, ice extent in March of the year of the return year here. So ice extent in the year of the return seems to have some importance in predicting run timing. Air temperature in king salmon in January and February of the return year, so a little closer to the season as well. Anyway, we see that there's a range of environmental factors that seem to have some importance in predicting run timing. Oh, the other thing I wanted to note is notably absent from that is precipitation. I thought, precipitation, high or low snowpack leading up to the season that sort of to some extent determines outflow from some of our river systems. I expected that would be higher in the batting order in terms of importance and sort of for Bristol Bay as a whole and across systems, at least up through the winter time period. It doesn't seem to be as important as I would have thought kind of going into this study. The other piece of sort of information we get, so the importance tells us which of these variables are important for or do a better job than others of predicting run timing. The other one is what is the shape of that relationship? So we can look at what are called partial plots. So this blue line here, and basically what this shows is across the range of our predictor variables. So this is the NPGO index in November. I have my little code here for November of the prior year. If that has a low value or a high value, so on the x-axis is low values of NPGO, on the right side of the x-axis are high values of NPGO, and on the y-axis is run timing. So later run timing, earlier run timing. So what this plot tells us is that run timing is fairly consistent up until you get to fairly high values of NPGO, and then we see this distinct sort of break point that seems to have some value in predicting our runtime to Bristol Bay as a whole. If you have NPGO values above this threshold, all of a sudden you go from kind of average run timing to earlier run timing, or at least that's the signal that we're detecting in these data. We can look at a range of these partial plots, same sort of thing. Again, for these kind of top predictors, the ones that have are most informative for predicting run timing. Some of these include things like the run timing 3 years ago. So in this case, if run timing was later 3 years ago, run timing is likely to be later this year. We have a couple of them that I'll highlight here. Again, as we saw before, when the NPGO signal in November of the year prior to the return, so thinking about 2022, that would be November 2021 when we were all having Thanksgiving dinner. In years where that tends to be a bit higher, at least above this threshold, run timing tends to shift earlier. With ice extent here, again, in years where we had, so this is March ice extent in the year of the return, in years where we have a higher ice extent, run timing tends to be a little bit on the earlier side, at least over a pretty broad range. And king salmon air temperature here in January and February of the year of the return, when we have warmer temperatures in king salmon in January and February leading up to the season, we tend to have a little bit earlier run timing. So as you said before, these squiggly lines tell us a lot. One, what the sort of shape and direction of that relationship is, and two, whether or not there's a kind of distinct break point. And that really is the value of taking this approach. So what have we learned? Well, there's a few key predictors that seem to pop out, whether we're talking about Bristol Bay as a whole or our individual fishing districts. Some of these broad climate indices seem to be associated with run timing. NPGO, the Pacific Decadal Oscillation. The prior year's run timing does seem to be important, depending on what the run timing was 2 or 3 years ago. That seems to have some predictive potential for what the run timing is likely to be this year. Ice extent out there in the Eastern Bering Sea at different periods in the year, and then of course this king salmon, airport air temperature is this sort of long-term time series we have describing air temperature conditions. So I'll say this work is still ongoing. We're exploring different methods. We're still bringing in different environmental variables that might be useful in predicting run timing. We're exploring what predictive potential we have kind of based on data that we can pull through May 1st versus, sea surface temperatures as we get closer to the season, later in May, beginning of June. Exploring those pieces are ongoing, but, our preliminary, fits of these models to the data suggest, Bristol Bay as a whole run timing might be a little bit closer to average compared to what we've seen in the last few years. Igigik, we've seen this pattern of late run timing, and it seems like it's going to be late again. Naknek Kvichak here as a district, seeming like it's going to be slightly late this year, but not as late as Igigik. And Nushagak maybe on the early side is kind of what we're seeing based on these fits to the historical data, as well as the conditions we've seen out there in the North Pacific in the lead up to the 2022 season. So with that, I really want to thank BBRSDA for their support and in funding this ongoing research, as well as the ADF&G scientists and technicians who work hard to collect all these in-season catch and escapement information and make them available, as well as NOAA and NASA for a lot of the ecosystem information that really goes into these methods. And I'm happy to take any questions if there's time.
Great. I see one in the chat here from Bert Lewis. Says, did you test model if salmon SPP abundance influences runtime? What about salmon size? Do smaller fish return later?
That's a good question. The answer, Bert, is no. I think that's a good one to put on the list, both in terms of abundance of other salmon out in the ocean. I know we might think that when there's more competition, kind of the benefit of sticking around out in the ocean for an extra couple of weeks to put on a little additional growth and feed, particularly if you've been competing with others, might be important. That's a great idea. Yeah, so Luke, that's a great question. So I was just looking at least at this point, at the Nushagak district as a whole. So on aggregate across the river systems. So I haven't broken it out by Wood or Nushagak River specifically.
Like a similar question about Ugashik, because that may be the same. Yeah. It just says Ugashik prediction.
Oh, let's see. Sorry, I'm scrolling back through. I would have to look up what the Ugashik prediction is for this year, but I think, slightly later than the average is what sticks in my mind, but I don't have the specific number in front of me. Should have thrown that in there.
Thank you.
Well, if there aren't any other questions, feel free to reach out, and I'll turn it over to Ray.
Okay, thanks a lot, Curry. Let me share my screen here. So I'm going to talk about a study we've done with funding help from BBRSDA on assessing the environmental footprint of the Bristol Bay sockeye fishery. The sustainability how sustainability has been interpreted has been expanded a lot in recent years. I mean, clearly, from a management perspective, the Bristol Bay fishery is quite sustainably managed. We have escapement goals, we have good enforcement system, but fisheries also, as all food production, have other environmental effects. And what we've done in this study is start to look at some of those with a particular focus on carbon footprint, because there's been a lot of interest in carbon footprint, again, both of fisheries, but also all food production. So I've partnered with two different research teams who are experts in this process. The process is called life cycle assessment, and that's really following everything it takes to produce a product. If in the case of carbon footprint, what's the carbon footprint of the fuel used in harvesting, in tenders, in processing, and in fact, in one of the studies, we looked at transport to markets. But we also were going to look at things other than carbon footprint. So there is a large and extensive literature on this for fisheries that goes way back. And so this is some of the historical literature on carbon footprint of fish harvesting. And almost all of the footprint on the harvest sector comes from fuel use. And this is a paper that reviewed, I think, over 100 different fisheries, looking at the amount of fuel used measured in liters per ton. So that's, this broke it out. The clear winner in most fisheries has been small pelagic fisheries, sardines, herrings, mackerel, and then a lot of variability across finfish, mollusks, salmonids, and then large pelagics tend to look a little worse or use more fuel, and then flatfish a little more, and finally crustaceans, shrimp, crabs, lobsters tend to look more poorly. When I first got into this back in about 2011, this was the kind of data that were available. And the data for salmonids were pretty high, 886 liters per ton. Now, most of these studies at the time were European studies, or certainly Atlantic studies. And so one of the things that I've been doing is we collected data from Alaska, and we're going to look at the Alaska salmon footprint specifically, and looking at both Bristol Bay and in one of the studies, Prince William Sound. What we did is we got data on fuel use from processors who supply fuel to their fleets, to their tenders, and also data on their processing. Fuel use for Bristol Bay certainly averaged much less than 680 liters per ton. That just the harvest sector alone, we got it in several forms. In some cases, it was split by harvest and tender, and others, different companies reported it as both harvest and tender. But you see, they came out about the same. The harvest was about 60 when done separately. Tender was about 75. When they were combined, it was 121. So, and then got the number there. Processing, that's a lot of the carbon footprint from processing is from electrical use as well. So I've translated that back into liters. Certainly in Bristol Bay, pretty well all of the processing uses diesel ultimately. but you see the numbers are very low compared to the pre-existing literature, 120 to 135 liters per ton for harvesting, a lot less than this 886. So we've got two papers working with two different teams. Each of these teams were experts in this process of life cycle assessment, which I'm not an expert on. So my end of things was to help collect the data on what goes into the process, to the catch and processing, and then to make sure they didn't do anything that, because of their lack of understanding the fisheries. So one team was this first paper is the purpose was to compare the greenhouse gas and other impacts of farmed Atlantic salmon from Norway to Alaskan sockeye and pink salmon. The LCA expert is Dr. Frederica Ziegler from a research institute in Sweden, and that paper's been submitted. And then I've also, and I'm not going to show results because they're quite similar, from another study I did with colleagues from Rockefeller University and University of Florida. So this is the basic result. So it's both sockeye, say Bristol Bay sockeye, and pink salmon from Prince William Sound. And now we're measuring the greenhouse gases as kilograms of carbon equivalent per kilogram of product. And so that goes from a low, let's take frozen Bristol Bay sockeye of about 1.7. And that's delivered to Paris, compared to fresh sockeye running about 5. And the difference there is totally transport. Fresh sockeye are put on an airplane, frozen sockeye go by ship. And that's a very big difference. And you see, there's not much difference between sockeye and pink. They're both captured very efficiently, have relatively little processing. You can see that it's split out. The orange is fishing for fuel. That's both fishing and tendering. The gray, the orange, the light yellow is feed for farming. And now why doesn't it show up there? I'm not quite sure. So I think it's quite small. For pink salmon in Prince William Sound, some of their carbon footprint comes from the hatchery program, but the pink salmon don't get fed very much. And then on the right-hand side, we have Norwegian farm salmon delivered to Paris. They all come by truck. So whether it's fresh or frozen, it's not very different. But you see the production costs for the farm salmon are mostly in the feed. And that is about 4.5 kilograms per kilogram. Some is in the farmed operation and not much processing, and some in the distribution. But certainly frozen pink and sockeye look much better than farm salmon. This is delivered to Europe. Even when Bristol Bay or Prince William Sound fish are put on an airplane, they still come in lower than farm salmon. Now, delivered to Los Angeles, obviously Alaskan fish look a lot better because now the transport costs are quite a bit lower for Alaskan fish, and the transport costs are higher for the Norwegian fish. So we've also looked at other aspects. There are other impacts. One of these is nutrient release. So nutrient release is a real problem for farming. If you look at the farm fish, you see most of the nutrient released is coming from from the farming problem, and that's essentially fertilizer used to grow the crops that that is used to feed the farm fish. In Alaska salmon, most of the nutrients comes from the processing, and that's largely the grinding up and discharge into the ocean of waste products. So the more that Alaska salmon processors start to use the waste products for fish meal and fish oil, the more that will come down. And I'll talk about that a little bit more later. Another standard output of life cycle assessments is what's called ecotoxicity, combination of pesticides. In fisheries, it really amounts to anti-fouling paint. And you see that fisheries always score very, very low on ecotoxicity. And again, Norwegian farm salmon, it almost all comes from the farming operation. And that's because pesticides, that is, you know, things are used to grow the crops that farm fish are fed. The area actually used, there's essentially, because sockeye feed themselves, there's really no area being used for sockeye. For pink salmon, there's a little bit because of the crops used to grow in the hatchery. The land use for farmed Atlantic salmon is largely the area used to grow crops. And you know, for farm salmon in general, it really is not the area where the salmon are farmed that really is the area that's used. It's the area used to grow the crops. In this paper, we've looked at how not only what are the impacts, but how they could be reduced. The first one, and we're starting to move that way for some of Bristol Bay, is to, if you can get hydroelectric power instead of diesel power, that really cuts down the processing greenhouse gas footprint. Full utilization of byproducts would greatly reduce the nutrient release from the processing stage. One of the big uncertainties we faced in our analysis was the amount of refrigerants used for the drift vessels and tenders, that very few fishermen were able to tell us how much refrigerant they used. And refrigerants, depending on which one, can be a pretty significant greenhouse gas. And then there's new technology called super chilling that will, in theory, allow fresh products to be delivered by sea instead of by air, which would really cut down the footprint of Alaska salmon delivered fresh elsewhere. So we did a couple studies on how much we could reduce the footprint by adopting all of these things. And so you see that that we could get it down to almost a kilogram of carbon per kilogram of product delivered to Paris, and well under that, more like 7.5 when delivered to Los Angeles. And just to wind up, just to compare a sockeye sandwich from a fast food processor or to what is being touted as the environmentally friendly form of food, that is the Impossible Whopper. That's a vegetarian imitation of hamburger. We're way under that, and now there's a big push for all of these artificial fish being produced from plant products. They're never going to come close to the real thing. And this study provides an opportunity for BBRSDA and the Alaska salmon industry as a whole to really advertise their products as one of the most environmentally friendly forms of food that we know. So thanks very much, and I'll take any questions and stop sharing. Let's see, should I look at the chat window or Q&A? Let's see. Liters per ton, gallons per pound. I have to do that backwards. so a liter is 3.8, 3.8 liters to the, so I have to do some arithmetic here.
Hey, Ray, while you're doing your calculations, the other thing, of course, that would reduce greenhouse impact is if they all went back to sails. And I heard Michael Jackson's just operating on a sailboat this year.
Is that right?
You are correct.
Have fun.
3.8 per pound, 220. Can you who sent that question in? Anonymous? Can you email me and I'll do that once I just do the arithmetic. But because almost all the other studies were in liters per ton, metric ton, that's the unit. But and it's really always the ratios. How are we compared to other things? And so for instance, the greenhouse gas footprint is lower than producing a kilogram of Alaska sockeye is lower than a kilogram of corn. It's really quite good. Let's see, a sane sockeye could be short duration multi. Oh no, that looks like that's a. Yeah, that's not a question to me. Should I look in the chat window? Where are the other questions?
Yep, I don't. There's some that's been coming in the chat, but I don't know that any are specific to this. Let's see.
Okay.
Yeah.
Well, as I say, if anyone has any questions, send me an email and happy to follow up.
Great. Yeah, thank you so much. Thank you all for making yourselves available. And yeah, I'll wrap us up here. But yeah, thank you, Chris, Daniel, Curry, and Ray. Your work is super important to us as fishermen, and we really appreciate you taking the time to interpret your findings and make it accessible to us as the fleet for our understanding and our use.
Hey, Francis, before we sign off, I think there's a really good comment here from Franz Schoenberg that Ray should answer.
Yeah, I do. I see that. The question if the fleet was all R507 or some refrigerant that scores low on ozone depletion potential, would that be something to advertise for the world? Yes, and unfortunately, we weren't able to get a good data set on what refrigerants they're using. The processors pretty well all use ammonia, which is really low. So that was, there wasn't a big, but some of the fleet and the processors seem to use a mix of some high impact refrigerants and some use low impact. And generally, everybody used so little, they just didn't have records on how much they had used. But switching. I think
one point for clarification, though, is the refrigerants are a greenhouse gas. The issues of ozone are basically in history. I think the refrigerants are mostly a concern for as a greenhouse gas now.
Yes, but the same thing's true. In fact, I think R07 507 might be a high greenhouse gas, but a low ozone. But there's among the refrigerants that are used, there's quite a bit of difference in their greenhouse gas refrigerant. And oh yeah, I mean, we didn't in our LCAs, we didn't look at ozone depletion. But sometimes LCAs do that. That's just another dimension on LCAs. But I think the big interest is on greenhouse gas. That obviously it's a concern because things have gotten warmer, and potentially that continued that may be a threat to Bristol Bay salmon, and it's if you look in the different groups like the pollock fishery recently did an LCA, really just calculating their greenhouse gas footprint, showing again that they're much lower than the existing literature on midwater trawl fisheries, that they've got quite a low greenhouse gas footprint. So I think that's where the promotion is going to take place in the greenhouse gas world.
Great, thanks for pointing that out. I missed that one. Let's see, I see a couple more questions in the Q&A that might pertain to other presentations.
Why don't you answer that aloud, Daniel, while you're typing in?
Oh, yeah. Yeah, there was one question there about data to suggest what the impacts of over-escapement are. And, you know, it is a concern that people have on their minds, but the reality is the data suggests it's really not a big concern. That, you know, what happens when you get up into the watersheds is that when there is big escapement abundance, a lot of those fish actually die before they spawn. So some of the concerns for you know, degrading the ecological potential of the watersheds doesn't seem to be borne out. So the issue of over-escapement is really an economic question. It's not a biological concern. And I realize that's controversial, but happy to pick it up with you if you want.
Okay. I see a question. The recorded presentation will certainly be available, and I hadn't asked you all presenters yet if your presentations would also be available as files. Is that possible?
Absolutely.
Okay. Yeah, so I will post it with the recorded presentation and links to the presentation, and they'll be on the BBRSDA homepage. There's kind of a column on the right, and there's like, I think it's recent presentations or something like that. It'll be there. If not later today, tomorrow, hopefully. All right. Thank you all so much. I don't see any other questions here.
Well, thanks everyone for your time, and good luck this season. And if you're bringing your boat back through Iliamna up and over the Williamsport Road, stop in and say hello. We'll be out there late season.
And thanks again for all of your support in the past and hopefully in the future.
Yes, thanks to Francis and Michael for hosting this and making the connection for us to make the presentations to the fleet.
Well, thank you all. I wanted to make the statement before we started, and I forgot. The FRI UW program was started in '46 because salmon runs were declining, and industry asked the University of Washington to step in and help to get these programs, get the runs back up to sustainable levels. And I'd say since 1946 till 2022, they've achieved that purpose and more. So they have a long and storied history, and they're continuing on with it. And the record runs that we're experiencing now are a direct result of all those years of research, as well as the world-class management that we have with our area managers. So I just want to make sure everybody knew that. And once again, thank you all for attending, and thank you, our panelists.